This is a follow-up to a video we did on creating a web service using the Metaspex framework. The web service is very simple. The code is on the text editor on the left of the screen. It's very compact. The purpose of the web service is quite simple. It is to receive a message from the client, take that message, append yourself to it, and reply. That web service is not doing any database I/O. It's very simple. However, it can be interesting to see the performance of that web service. So first of all, I'm going to show you that we are running Nginx. So we are running a few processes here. That's the way Nginx has been configured. It's running a number of processes. We could have threads instead. We can send a web service call to one of these, and Nginx is going to choose whichever worker process it wants. So I'm going to retrieve it. When I do this, we are actually going through port 8080, which is the way Nginx has been configured. We are sending a message. Here it is hello, and it is replying hello yourself. I could use a different string, of course. Bonjour yourself. Okay, so in order to measure performance, the first thing you do when you are working on the Unix-like system is that you use the time utility. So time is going to measure the time spent by the utility I'm using here to send a web service call, which is curl. So here it is. I have the reply, but I have additional information, which is showing the amount of real time spent by the command, the amount of user time, and the amount of system time. So the first figure is not very, very precise because the web service is executing extremely fast. We are at 8 milliseconds. It's not really interesting for us because if we want to do capacity planning for the backend, the client is going to run somewhere at the other end of a network, and the backend is going to spend time executing the web service. So in order to do this, Metaspex supports something different from time, and I can add the query string right after the web service endpoint name, and the query string is T. So T is instructing the Metaspex backend to measure the time spent from the moment the web service is received in the backend, excluding the network lag, to the moment the web service is replying to the client with a JSON object. So when I do this, I'm going to have the total real time in the backend, and I'm going to have as well the CPU time, which is more interesting for capacity planning, spent by the application itself, the web service, to execute the body of the web service. So I'm going to run it. You see that I have, like with time, additional information. I have my reply, but a key has been added. It's arrow-based T, and it is a JSON sub-object to the reply. And inside this sub-object, I have a key, which is total, which itself contains the real time spent in the backend. So if we were doing database I/O, for instance, that would be included. And we see as well the CPU time spent in the application tier. So we see two numbers. One is 15,760, and the other one is 14,660. So what is the unit of this? So these are not seconds. These are actually nanoseconds. As a reminder, a nanosecond is 1/1,000,000th of a millisecond. So it's really tiny. In order for us to see the cost of the execution of that web service, we need to translate this into seconds. So this is 0.0146 milliseconds. So I'm going to use my calculator. 0.1446 millisecond. And I am going to invert it. which means there are 68,500 of these in 1 second. So it means that there is space in the backend, in the processor, for 68,000, in excess of 68,000 times this web service call every second. So I know people are going to tell me, you cannot do this kind of math, it's not linear, and so on. They probably have this reaction, mostly because they are using a garbage-collected programming language in the backend. And garbage collection is actually hampering that kind of vertical scalability, because it does some magical things on the memory in order to find lost memory and collect it. The linearity is much, much better when you are not using a garbage collector. In this case, we are not, and we are using instead reference counting, and we have a very specific algorithm, because we are using ontologies, that allows to create cycles between objects. So that is quite unique. Reference counting is usually not allowing to do any kind of cycles. So we can do reference counting and cycles at the same time. So it means that the math I just did is not completely accurate, but it's much, much, much closer to this than if we were using a garbage collector. So we are doing 68,000 of these per second, or close to it. And as a reminder, this is per core. So if we have a 16-core machine, we can do 16 times this. This is a 16-core machine, so I can actually absorb a lot of these web services call every second. You understand now why we don't need a lot of complexity when defining a backend using Metaspex. The infrastructure required is very, very small. As a reminder, the module we are using here, which is the complete application, is 10 megs, and we are loading it as a module in Nginx. It's a shared object, so it means that it is loaded only once in the backend. No matter how many processes we are using, here we are using a lot, the shared object, the 10 megs, is actually loaded only once. So you have an incredible amount of throughput with a Metaspex backend, and the memory footprint that you need is very small. Also, knowing that even when it includes an interaction with the database, web services typically execute within a total amount of time in the vicinity of 2-3 milliseconds typically. It means that even if you add network lag, let's say worst case scenario, running a backend in the US and accessing it from a remote place such as Australia or Southeast Asia, you add 250 milliseconds, we're still within instant response time. So I hope this showed you that even with this toy example, a Metaspex backend is extremely frugal, extremely fast, and this is due to the combined use of layered abstractions and the fact that we are using the C++ programming language, which is allowing for zero overhead abstraction. So you get the best of many worlds, you get a ton of productivity, probably something which is higher than anything that AI is proposing, and at the very same time, you get a ton of performance. Thank you.